Okay. Uh, okay, sorry. Okay, so in Cal 1, you learn when a definite integral is given, how to find the approximate, by using limit of Riemann sum, you got an approximation to the integral. So let's recall how do we do the Riemann sums, because we need that knowledge to in this section too. So the first step is we divide the closed interval a to b into n subintervals. Okay, so that's the first step you do. So how to do that? So this is called the subinterval, we call it as length. So length, we denote it as delta x is equal to the difference of the closed interval, that is b minus a, divided by n. So that is n is the number of subintervals. And then we have the definite integral of x dx. This is approximately equal to, this is a sum of the y values, that is f of x star delta x. This is the Riemann sum. What is this xi star? This will be any point in the ith interval. What is the ith interval? So ith interval you will get like this: x minus 1, x. So this is any point in the ith interval, and delta x, we define how to find the delta x. It is b minus a over n. N is the number of subintervals. Okay, so then if this xi, so this xi, if this point is the left endpoint, what does that mean? So if you draw the real line and this is your ith interval, so in the ith interval, this is your left endpoint. This is called the left endpoint. Okay, so if you use the left endpoints, then your definite integral is, we approximate, and this sum we denote it by capital Ln, and this is equal to the sum I to n f. So the left endpoint is x I minus 1 delta x. I'm writing this because in your homework questions, you are required to find the sum by using the left endpoint. So make sure you take the notes. And then this is if you use the left endpoint. If this xi star is the right endpoint, then your definite integral is approximated. If you use the right endpoint, you denote that as capital Rn. And this is the sum of the f at xi. So xi delta x. So here, if I draw again the ith interval in the real line, this is x minus 1, this is xi. Now you use this point, right hand point, okay, to find all the y values. And then you take all the sums of that y values, multiply by the length, and then you can find the definite integral. Okay. So let's now this is the this is a revision, and now let's study. Let's find the new part. This is called the trapezoidal trapezoidal rule. Okay, so this again, this allows you to, so this is the this allows you to find or estimate the value of a definite integral which is area under a curve. So let's do this by an example. So example 1, you have to find the definite integral. Now 0 to 10 x squared dx. So let's see how to find the definite integral by using the trapezoid rule. And then let's do the exact value, because we know how to find the definite integral of this question. So let's see whether it is overestimated or underestimated. So estimate the area under the curve from x is equal to 0 to x is equal to 10. Okay, so let's first draw and see. So y is equal to x squared, and this is x is equal to 0 to x is equal to 10. So that means the right, we take only the right side of the graph. So this is y is equal to x squared graph. So if I draw it, so the idea is we need to find the area of this part. Area. Okay. So let's find this by using 5 rectangles. So let's find 5 rectangles. That means n is equal to 5. Okay, so the step 1 is to find the length of the rectangle. So step 1 is you need to find the delta x. Can you all find the delta x and tell me what is the delta x? So n is equal to 5. 2. Yes. So, yes, very good. So, how do we find the delta x? That is b minus a over n, like we did in the beginning of the class. So, b here is 10 minus a is 0 over 5. So, 10 divided by 5 is 2. So, the length of a subinterval is 2. So, if we draw the real line, and x is starting from 0 to 10. So now you have 5 subintervals where the length is 2, 8. Okay. So the difference of the what we learned before and now in this rule is when we find in the left end point, we use only 0. So because if we take this subinterval, we take this point, right? If we take this subinterval, we took this point. If we take this subintervals, we take this point. If we take this subinterval, we take this point. And if we take this subintervals, we take this point. So even though you have 6 points, if we take the left end point, we only consider the points 0, 2, 4, 6, and 8. Only 5 points. Okay. Then similarly, can you tell me what are the right endpoints if we use the right endpoint rule? What are the right endpoints we use? By looking at the, yes, really good. So it is 2, yes, 2 is also included. So 2, 4, 6, 8, and 10. Okay, so again, only 5 points we use. What about the midpoint rule? Midpoints. So what are the midpoints of these subintervals? What is the midpoint of 0 and 2? What is the midpoint of 2 and 4? Yes, good, Tyler. Very good. So it is 1 because midpoints are these points. Okay, so here it is 1. Here it is 3. Here it is 5. Here it is 7. And here it is 9. So midpoints we use 1, 3, 5, 7, and 9. So here you see in all these 3 cases, we use only 5 points. Okay. So the difference of trapezoid rule is we use all the 6 points. Or these 6 points means we take all the y values of these 6 points. That's the difference. So for trapezoid rule, rule, we use all 6 points. Okay, so that's the difference comparing to other methods. Okay, now let's learn what is the formula for the trapezoid rule. So the formula for trapezoidal rule is, so trapezoidal rule we name is at capital N, capital Tn. So this is equal to delta x over 2. Here the delta x is again the length of a subinterval. And This is in the brackets. First term, it is fx0 plus 2fx1 plus 2fx2, like that. This is going, and 2fxn minus 1 plus fxn. So this is the formula for the trapezoid rule. Okay, now just notice that you see, so the first term and the last term in the trapezoid rule, we don't multiply by 2. Okay, so that means in a real line, the first point and the last point of the y values, we don't multiply by 2. But all the other points, you see, we multiply by 2. Okay, so that's how you remember. So the first value and last value of y values do not do not multiply by 2, and all the other y values multiply by 2. Okay, so let's do this question. So we have to find 0 to 10 x squared dx, and we took n is equal to 5, and so let's use the formula now. So the formula is t n is 5. So delta x we found, so that is the first step, b minus a over n. So 10 minus 0 over 5, that is 2. So 2 over 2, and remember we draw the real line, and the first one was x is equal to 0, x is equal to 2, x is equal to 4, x is equal to 6, to 8. 6, 8, and x is equal to 10. Okay, so the first point, the y value of the first point, we don't multiply. So we just write f0 plus, and all the y values of these points, we have to multiply by 2. So f at 2 to f at 4, 2 multiplied by f at 6, 2 multiplied by f at 8, and the last point also we don't multiply by 2. So this is the trapezoid rule. So can you tell me what is the value you get? How do you find a value? So here, if we use, let's say, f2, so our function is f at x is x squared. That means when you input x, your output is x squared. So if the input is 2, your output will 2 square. Okay, so like that, can you find what is the area? 336, 340. Let's see. Yeah, we have some answers. So let's 300. Yeah, I think most of you got 340. So let's do the calculations. So 2 or 2 is just 1. If 0 is 0 squared is just 0. 2. F at 2 means 2 to the power 2. 2 squared plus. F at 4 means 4 squared. F at 6 means 6 squared. F at 8 means 8 squared. And 10 squared. So 1, 0, 2 squared is 4. 4 multiplied by 2 is 8. 4 multiplied by 4 squared is 16. 16 into 2 is 32. 72, 128, 100. So we get 340. Okay, so if we use the trapezoidal rule, we get 340. I saw many of you got 340, so good. Okay, now let's see what is the exact value. Okay, now find the exact value. Find the exact value. 0 to 10 x squared dx. Can you find what is the exact value? So here I should write a note. So this is the approximate area under the curve. 3. Yes, good, very good. So let's see. Let's wait for others. Mm-hmm. 1000 divided by 3. Yeah, what is 1000 divided by 3? Mm-hmm. Yeah. Okay, so let's see. So this is equal to, how do we find? The antiderivative of x squared is x cubed over 3. And we have the upper and lower limit as 0, 10. So if we substitute, this is 10 to the power 3 over 3 minus 0 to the power 3 over 0. So 1000 divided by 3 is 333, 33, like that. Okay, now you see, it is kind of very close, right? Very close, 300. This is our approximation after use the trapezoid rule. This is our exact value. So this 340 is very closer to 333.33. Okay, so compare, if we use the left hand rule and the right hand rule or the midpoint rule, just if you want to try, you can try. But so can we use the trapezoid rule for any approximation problem, or are there any? So there is another approximation. I will do it later, like after this. So comparing to the left-hand side, right-hand side, and midpoint, trapezoid rule is, it's a very good approximation. Okay, I'll do another one after this. But comparing to the before 3, this is a good approximation. So this is a good approximation. So comparing to right, left, and midpoint approximation. Yeah. Okay, let's do another one, another approximation, that is a Simpson's rule. So let's find that next approximation rule, and this is called the Simpson rules. Simpson's rule. So the Simpson rule, let's do this by an example again. Use Simpson rule. To approximate or to evaluate the integration from 2 to 10 x cubed dx. Okay, so then let's see what is the formula again. The formula for the Simpson rule. Formula. This is Abra. So here we denote the Simpson rule, Simpson rule by capital S N. So capital S N is equal to now. This is kind of little bit tricky. Delta X, again, it's the length of the subinterval. Divide by 3. Now, let's see what is in the parenthesis. This is fx0, the first point, and 4fx1, 2fx2, again 4fx3, 2fx4, like this, and we add 4f of xn minus 1 plus f at xn. Okay, so what is the difference between this and what we learned before? Here you see there is 4, 2, 4, 2. Always there is a pattern, right? So here, let's see what is the difference. So again, but like the trapezoid rule, the first and the last y values doesn't multiply by any coefficient. How to remember this Simpson rule? And the second, does the second to last? Yes, second to the last is 4. No, the second to the last is, this is 4, and this one is again 2. F at xn minus 1. So I will write that as a note. So here, start by always 4 by 4 and alternate 2 and 4. 2 and 4. So let's do, you will understand when we are doing the example. So first one, we don't multiply by any constant. First one and the last one. And the second point, that is fx1, we start by multiplying by 4 and then we alternate 4, 2, 4, 2, 4, 2. The one before the last one, that is this one, it should be 4. So let's do to understand that, let's do this example. So first step, can you find what is delta x? That is step 1. What is delta x? Is it 4? What is delta x? Here we have 2. Remember the lower limit is 2, the upper limit is 10. Oh, sorry, I forgot to mention the n. So n is equal to 4. We are going to find n 4 subintervals. 2. Yes. So 2. So then the length of the subinterval is 2. So how? So b minus a divided by n. So b is 10 and a is 2 divided by 4. So L divided by 4 is just 2. So the length of a subinterval is 2. Okay. So if we draw the real line, so the first one is starting from 2 and the last one is 10. Then what are the other points? That is, this is x is equal to 4, x is equal to 6, and this is x is equal to 8. Okay. And in Simpson's rules also, like trapezoidal rule, we use all the points. Okay, we don't, we have to use all the points, like the trapezoidal rule. So here also we use all the points, like trapezoidal rule. Okay, so can you find the S4 by using the formula? So delta x is 2 over 3. So here fx is x cubed. That means whenever you input x, output is x cubed. So fx0 plus, we start from 4, fx1, I mean fx. So let's first let's just substitute the values, then it will be easy. So first point is f at 2 plus 2 f at 4. Sorry, 4 starting from we start from 4, so 4 f at 4 plus 2 into f at 6, and we alternate. Then next one is 4 f at 8. The last one is f at 10. So we start from 4 and then we alternate 2, 4, 2, 4, 2, 4. Here we have 2 and 4, but the last ones we don't multiply. It's just f at 2 and f at 10. What is the area? So we must have an even amount of, yes. And find the exact integral. Mallory, yes, let's see for others. We have one answer. Mm-hmm. Okay, I see many correct answers. Okay, so yes, good. I see many correct answers. So 2 over 3, f at 2. So that means 2 cube, 4 multiplied by 4 cube, 2 multiplied by 6 cube, 4 multiplied 8 cube, and 10 cube. So this you will get 2496. Then what is the exact value of this? Sorry, 2 2 to 10. 2 to 10. Yes, so you will see this exact value is also we get the same answer. But this is because I took this example, you get the same answer because this is like a rare case. This is a rare case where the approximation and the exact integral is same. But in when you are doing the homework questions, you will see always the Simpson rule is kind of little bit, sometimes it's overestimated, or in some examples it's underestimated. But this is also very good approximation. So the trapezoid rule and the Simpson rules are very good approximation. So you can use trapezoid rule or the Simpson's rule if you don't know the exact uh, the exact antiderivative. You can use these two approximation to approximate the integration. So comparing to comparing to trapezoid rule and midpoint rule, Simpson's rule give better. You will, when you do the homework questions, you will see it's very closer to here also. It was very close. It's equal. So comparing to Simpson rule, comparing to trapezoid rule and midpoint rule, Simpson rule give better approximation. And you will see in the homework questions, most of the times, your exact answer will be in between the trapezoid rule and the Simpson's rule. Okay, but if you like, you can choose any method, trapezoid rule or Simpson's rule to approximate, because both of these two give good approximation. Okay. Okay, so in this section, I assigned only 5 questions because you have to do more calculations here. So only for homework, only 5 questions are given, not 10. Uh, so we'll move on to the last section of this chapter, because you will, I think in the syllabus, you see we are getting our first exam on this Friday or Monday. I'm not sure about that. So I have to check again. But definitely by tomorrow, I will send you a review questions, practice exam questions. So if you thoroughly go through the practice exam questions, your exam one will be similar to your review questions. Okay, so I will give you by tomorrow. So let's start the next one. That is, I think 7.8. Improper integrals. So in these sections, we are going to learn how to integral these kind of integrals. Yes. What is the difference here you see? What is the difference of this integral and infinity? Yes, good. So here you see the upper limit here. This is an infinity. Okay, so until now we learned definite integrals where we had upper limit and lower limit as exact numbers, right? So it's on 2 or any number. But here you see it is a infinity. So that so let's see how to solve these kind of problems. And also the other question is which is examinable is whether this integral is convergent or divergent. Okay, so how to find that? How to find whether it is convergent or divergent. So if we get a note, so when we are finding the integration, if we get a finite number, so if we get finite number, then we say that this whole integration is convergent. So then we can say if limit exists, because limit exists means when you take the limit you will get a number, right? So if you get a number, if you get a finite number, then we say it is convergent. So when you take the limit, and limit exists means when you take the limit, if you get a number, then we say it is convergent. But if you get the infinity, if we get infinity, that means the limit does not exist. So that means we say this whole integration part, this is divergent. So your integral will be divergent if you get an infinity as a number. Okay. Okay, so this method, this behavior, we call this whole thing as improper integral. So that means if the lower limit or upper limit is equal to infinity, we get a convergent or divergent thing when we substitute the lower limit or upper limit, then we say this whole thing as improper integral. Okay, now let's see how to solve these kind of problems. Okay, so the first thing you have to write is, first replace your infinity with some variable. So let's say, so throughout my example, I'm using t, variable t, but you can use any variable. So first replace infinity with the variable and express as a limit. So this means if I write it, so let's say you have to find 0 to 0 to infinity 1 over x dx. But now I'm going to replace this by t And I'm going to write this as a limit t goes to infinity, whichever the variable you use. Here t goes to infinity, and the other parts are same, 1 over x dx. Okay, now this one we can solve, right? Because this part is a definite integral, right? We know how to solve definite integral. Okay, so can you find what is the antiderivative of 1 over x? What is the antiderivative of 1 over x? Ln x, okay. So let's write that. So antiderivative of 1 over x is ln x, but we have now upper limit and a lower limit, so that is 0 and t. So this you will get when you substitute ln t minus ln 0. I think I did a mistake. So I'm sorry. This should be. I'm so sorry. This should be. The lower limit should be just 1. So I'm sorry. There is a mistake here. So the lower one is just 1. This one. This one here. Okay. Okay. So now let's see by the limit properties. Ln t minus limit t goes to infinity ln 1. Okay, so ln 1, this is always 0. L1 is 0. So this whole limit is equal to 0. So we have limit t goes to infinity ln t. Okay, so ln, when t is equal to infinity, ln infinity is infinity. So what is this? Is it a divergent or convergent? It is divergent because we get infinity. This is divergent. Okay. So let's do another example where we get a convergent part. Up to here, do you have any questions? Are you all okay with improper? Okay. Okay, so let's do another example. Example 2 is you have to find 1 to infinity 1 over x squared dx. Okay, so let's write this. So we have 1 to do. Let's write. We'll always have will a no, in this example a is just 1. It's not always because it is 1 over x squared. In this example which I'm using, a is 1. Okay, it's not always have to be 1. I will do another example where you will see a different value, but here it is just 1. Okay, I'm doing this because of a purpose. I will explain why I'm taking a is equal to 1 here. Okay, now let's write this in limit terms. So the first step, we are going to write it. 1 over x squared dx. So here limit. So first we replace infinity by t. This is 1. And t goes to infinity. 1 over x squared dx. So can you all find what is the integration of this part? What do you get for this? ln x, not ln x. Can you all check again? Yeah, I think yes. Yes. I see many correct answers. So let's see. Just forget about the uh, upper limit and the lower limit. So just let's first find what is 1 over x squared dx. So this you can write it as x to the power -2, right? And then we just use the power rule. So here, this is -2 plus 1, -2 plus 1. So it is x to the power -1, -1. Okay. Plus, there is plus c, but here in improper integrals, we don't consider the constant. Thing. Yes, yeah, just a second. Okay, can you see the screen now? Okay. Okay, so it is there's plus c, but in here improper integrals we don't consider about this constant, so you can get rid of this constant c when we are calculating, when you are taking the limits. So here you have -1 over x. Okay, now let's use this in the problem. So this is equal to limit t goes to infinity. -1 over x, 1 t. Okay, so just substitute. This is -1 over t minus -1 over 1. So limit t goes to infinity, -1 over t plus 1. Okay, what is this whole thing? When t goes to infinity, what is the limit of this part? 1 over t. 0, yes. So whenever you get 1 over infinity, this is always 0. So this part is 0. So remember, always when t goes to infinity, if you have 1 over t, this is equal to 0. That means whenever you divide 1 by a very large number, it is very closer to 0. And eventually your answer will be equal to 0. That's the idea. So this whole thing is equal to 0 plus 1 is 1. Okay, now is this convergent or divergent? Convergent, because this one is a number or a finite number. So this whole integration is a convergent. So we say it is convergent. Okay. Okay, so then we are going to write like a note. So here, next, we say P series. So P series, this is important to remember you because in the future, in finite numbers, when in some future chapters, you will need this P series one. So remember this one. So this means if you have to find the integration 1 to infinity x to the power p dx. Okay, if this p is greater than 1, always your integral. This integral is convergent. And if p is less than or equal to 1, this integral will be divergent. So you can see by the example which we did from example 1 and 2. Remember in the example 1, we did p is equal to 1. Okay, we found 1 to infinity 1 over x dx. We found this is to be divergent. Okay, so whenever p is equal to 1 or less than 1, always that integral is divergent. And when p is equal to 2, we found that this integration is convergent. So that means whenever p is greater than 1, your whole integration, your whole integral part will be convergent. Okay, so this is a thing that you have to remember, the p series. Okay, let's do an example from this one. Example, let's find what is the integral of 3x plus 1 to the power 2 dx. So you have to check whether it is convergent or divergent. Okay. Whenever we see this one, you can see this is kind of similar if you have this whole thing. So this is kind of similar to this one we did, right? X1 of x squared dx. Anyway, this in the inside it is 3x plus 1. But this kind of similar to this one, right? 1 over x squared because of this power. So we can just comparison. We can take a comparison between this, and straight away we can say this is convergent by comparison. Because it was similar, because this one is similar to what we did here in P series. But let's find whether this is true. So can you find by yourself whether it's convergent or divergent? This is equal to, we can write, what is the first step? We can write this integral as t goes to infinity, 0 to t, 1 over 3x plus 1 square dx. Can you use your integration substitution knowledge and find this? What is the substitute? How do we solve this? Are we going to use the substitution or what? What technique? Yes, very good, Lexi. So we are going to use the U substitution. Okay. So by U substitution, so we will use substitution. U is equal to 3x plus 1. So what is du? 3. So 3 dx. So dx is du over 3 dx. Okay. So without we just forget about the lower and upper limit part. Just find what is the um, integration of this one. What is the integration of this one? What do you get? Negative 3. Yes. Yes. Let's wait for others too. Yes, very good. Lexi, just check. There should be a constant in front. Mason. Yeah. Yes. Yes. Yes, Mason. Good. Okay, so let's start. So we can write this part as 1 integral 1 over u squared dx is du over 1 3 because of this 3. So this means this is, if we take this is u to the power negative 2 by using the power rule, we can say this is u to the power negative 1 plus c, but we don't, when we take the improper integral, we just don't care about the constant. So you will have negative 3 into u is 3x plus 1. Okay. Okay, now let's use this one to find this. So this is equal to limit t goes to infinity 0 to t negative 1 over 3x plus 1. Okay, dx. Okay, so let's use I'm sorry, so this, so no. This is your answer because we found the integration of 3x plus 1 to the power 2x, 3x plus 1. Okay, then we use the lower limit and upper limit, that is 1 to t, sorry, 0 to t. Okay, then let's use this. So negative 1 over 3, 3t plus 1 minus negative 1, 3. 3 multiplied by 0 is just 0 plus 1. Okay. Now, I'm sorry, here it should be. So the question was here, you see it is, there's a 1 here, sorry. There's a 1 here. So it is 1. The lower limit is 1, sorry. So it should be 1. 1. So this is 3 multiplied by 3 is just 1. Okay. So what is the answer you get here? Limit t goes to infinity. This is 3t plus 1. Here you will get plus 1 over 12. What is the answer you get? 20. What is under the limit? Under the limit. Under the limit, it should be. This is t goes to infinity. T arrow goes to infinity. T arrow goes to infinity. Okay, so here you get 1 over 12. What about this answer? What is this? Kilometer, yes, 1 over 12. Yes, very good. So, yes, we get negative 1 over infinity. So, this whole thing becomes 0 plus 1 over 12. This is 1 over 12. So, this is the answer. If you don't understand still how we got 0 here, how do we get 0 here? Because you can, t goes to infinity, you can change this 3t plus 1. You can multiply both by 1 over t and 1 over t, both numerator and denominator by 1 over t. So here then you will see t goes to infinity. Numerator you have 1 over t. In the denominator you will get just 9 because 3 multiplied by 1 over 3t multiplied by 1 over t, this get cancelled. So 3 multiplied by 3 is just 1. And here you will get 3 over t. So whenever you take, like I said, the limit of 1 over t is just 0. So whenever you take this t goes to infinity, this is numerator 0 divided by 9 plus 0. So that is why 0 divided by 9 is just 0. That's how I get 0 here. Okay. Okay, so you get 1 over 12. Is it convergent or divergent? Convergent. Okay, so this is because we get a finite number, we say this is convergent. Okay, so So we proved that this is convergent, but like I said before, if we comparison, if we see this as, because 1 over 3x plus 1 to the power 2 is kind of same as 1 over x squared, right? Because the lower limit and upper limit are same. So we can take the comparison and say straight away, without solving or without proving, we can say this is convergent by P series. By P series, we can say straight away this whole thing is convergent by comparison. Okay. Okay. So I'm going to do so we have to, so there is another part. It will take some time because I don't want to do it today, the comparison test for improper integrals, because it's like the end of it's the last part of the class. I want to begin the comparison test for improper integrals in a new class. So I'm not going to do that, but I'm going to do some bounds that we have to do, error bounds in the last section, because this is just substituting numbers. So in the last section 7.7, where we did trapezoidal rule and Simpson's rule. We see there is an error, like okay, there will be a small error in the exact value and the value we get from the trapezoid rule or Simpson rule. So to find that error bound, we have a equation to find the error bounds. So I'm just doing the error bound for trapezoidal rule today, and in this class. So how to find the error bound for trapezoidal rule? So when you take the second derivative of f of a function, by the second derivative of function, this measures this measures how fast slope of your y is equal to fx changes. So this is the idea of the second derivative of a function. So second derivative of function means we can measure how fast the slope of the curve changes. So suppose we take a bound. That is, we take the absolute value of the second derivative, and suppose this is bounded by a constant. So this means whenever you write something like this means it's bounded. Bounded means it's always when you take the absolute value of the second derivative, it is under a certain constant. Always, whenever you substitute x values, always you get a value which is less than or equal to a constant k. That is the idea of a bounded. For when x is between a and b, so if if ET is the error bound error in the trapezoid rule, then the bound of, like I said, the bound. So if we denote the error of the trapezoidal by using the trapezoidal rule, the error by ET, this is always bounded by K B minus AQ over 12n square. Okay, in this part you will not, there is no homework questions from this part. This is just to take an idea what is this error bounds are. So that's why I kept this part at the end of the class. So to find the error bound, this is the formula of an error bound to the trapezoidal rule. So the idea is K we found from it is this value where the second derivative is bounded by that constant. And let's do an example for this. If your function fx is x squared, can you all find the second derivative of f? What is the second derivative of function f? Second derivative. So second derivative is just, so the first derivative is 2x. Yes, very good. So the second derivative is just 2. Okay, so we are finding any number. So this k can be any number. Okay, so k can be, so when you take the absolute value of the second derivative and is less than equal to k, this k you can take any number like k is equal to 2 or k is equal to 3 or 1000 or any number. But if you take the, like when you take the lower value, the like when it is very closer and when it is very low, then you will get more accurate numbers. So let's just first see. So if, let's say if k is equal to 3 and a is equal to 0 and b is equal to 10 and also n is equal to 5, can you find the error estimate? What is the error estimate you get? So error estimate means you have to find the absolute value of ET here because we use trapezoidal. It's 625. Let's see. So let's see. So 300 is 100, 600. Okay, let's see. So our error estimate bound is this one. So k is equal to 3. B is 10 minus 0 to the power 3 over 12. N is 5, so that is 5 squared is 25. So this is equal to 3 into 1000, 12 into 25. So I get this is, no, isn't it 10? Yeah, yes, it should be 10. Yes, good. So the error bound is less than equal to 10. Okay, so let's do an example so this is the error bound. So if they're asking if you have to find the error bound for the trapezoidal rule, this is the way you have to use this formula to find the error bound of the trapezoidal rule. So let's see why we have to find this kind of error bound. By using the Simpson rule. So Simpson's rule, error bound is this. Error bound is so here suppose in the Simpson's rule you have to find the fourth derivative and it is bounded by k for a x is between a and b if capital ES is the error bound. It's error involved in using Simpson's rule. Then your error bound is, in Simpson rule, it is k b minus a to the power 5 over 180 n to the power 4. So let's use an example to understand why we are doing this error bound. So example, how large should we pay n this is n in order to guarantee that the Simpson's rule approximation of for 1 over 2 is 1 over x dx is accurate to within 0.0001. So these are the type of questions that you will get. This is not examinable because this is, I don't examine from this part and you don't get any homework from this. So, but just to know, these are the things called like how when you have an error, when you approximate Simpson's rule, the error you get and you need to find the error bound. This is how you find the error bound for Simpson's rule. Okay, so let's just practice this question for your knowledge. So first we need to find, because here you see we need to take a constant, we need to find the fourth derivative of f. So can y'all find when So your function here it is 1 over x. So can you all find what is the fourth derivative of 1 over x? This won't be, this won't be in the test because um, it's not in the test, don't worry. This is just for your knowledge sake. So what is the fourth derivative of f? Just to practice, what is? No, no, Kyler. Can you check again? Yes, we have some answers. 1 over 30 x to the power 5. 24 x to the power 5. Okay, Kiyomi. So let's see, we have some answers. So first derivative is, we can think this is as x to the power -1. So first derivative is -1, -1. So this is -1 into x to the power -2. Okay, so this is the first derivative. Then second derivative, you differentiate this. So here you have -1, and you take this power again by the power rule, and here this is, you will get -3. Okay, so here 2 into x to the power -3. So what is the third derivative? Now again by the power rule, so you take -3 here, and now this will become x to the power -4. Okay, what is the power rule? Power rule is n x to the power n-1 by using this power rule. Okay, and then fourth derivative, because we need to find the fourth derivative. So 2, -3, -3, x to the power -5. It is -24. Sorry, positive, because negative multiplied by negative is positive. So it is 24 x to the power -5. Okay, yes, I see many answers. So 24 x to the power 5. Okay, now what does it in Simpson's rule says? Now we need to take a bound. Okay, we need to take the bound of the fourth derivative, which is less than or equal to k. Okay, so this means 24 to the over x to the power 5. So here we have to, because they don't give, they haven't given k here, we have to take a k, like we have to assume a k. So how do we assume a k? We can check by looking at this. because we know x is between 1 and 2. Okay, then x is between 1 and 2. What about 1 over x? 1 over x should be, then we flip this in inequality, so it is like this, right? 1 over x should be between 1 and half. So we can take from this one, 1 over x is less than 1. Okay, so that means 1 over x to the 5 also is, we can say it is less than 1 because it is, this 1 over x is less than 1. So straight away we can say, we can take this one as x to the power 1 over 5. This should be less than 24 over, because it should be less than 1, so it should be less than 24. So this we can assume k to be 24, right? Did are y'all okay how I got this idea? So because x is between 1 and 2, I can flip the inequality and say 1 over x is between 1 and half. So from this part, I can get a bound for this. Because 1 over x to the power 5, we can take a bound, and we can say this whole 24 over x to the power 5, the absolute value of that, it should be less than 24. So k can be 24. Okay, if k is equal to 24, if k is equal to 24, the error bound for Simpson's rule is less than equal to, this is the formula, b minus a to the power 5, 180 to the power n over 4. Here they have given the error bound is accurately, this is the error bound they have given. So we can just substitute this 0.0001 and k is 24. B minus A, what is our B minus A? B, it is 2 and 1. So it is 2 minus 1 to the power 5, 180 to the power n to the power 4. Okay, so 0.0001, 24, 2 minus 1 is 1, 1 to the power 5 is 1. This divide by 180 to the power n to the power 4. Because the idea is we have to find a n value. So by solving this, we can say n to the power 4 is greater than 24, 180, 0.0001, and n is, you will get approximately 6.04, like approximately if you do the calculation. So the idea is, if n is greater than any number, if n is greater than this number, you will get the error will be within this 0.0001. That's the idea. So this is an example how you use these error bounds of trapezoidal rule or Simpson's rule. So for Simpson rule, because we say n should be an even number, we can say n is equal to 8 here. N is equal to 8 here for Simpson. We can say n is a 8 is a good one for Simpson's rule. So that's the idea. Okay, so I'm going to stop here, and I will do the comparison part of 7.8 tomorrow. And tomorrow I will give you the review for chapter 7. And also, if you want the notes of chapter 7, let me know. If most of you want the notes, I can uh, put it in the Moodle. So yeah, that's all for today. If you have any questions, you can say. See you tomorrow. Mhm.